All right, so we've seen now how we can use the Nernst equation in order to calculate the E of a cell under non-standard conditions if we know the E of the cell standard, because we can look up those values on a table, and if we know the number of electrons that are being transferred, and if we know the reaction quotient Q, we can simply plug it into our equation and we can calculate E of the cell under those non-standard conditions. Now, the examples that we looked at were where we had two different half cells that had different elements, different types of electrodes in it. So we had a zinc and a copper, or a silver and a cadmium, or in all of the examples that we looked at, Q here, our reaction quotient, involved two different elements. So for example, the one that we did previously, the product here would be the cadmium concentration, and then the reactant would be the iron 2 plus concentration. We plug that into our reaction quotient Q. Now, because the E of the cell, electrode potential, depends on ion concentrations, it is possible to construct a galvanic cells composed of two half cells that are made up of the same material. So in other words, both cells could have zinc in them, but what's different would be the differing ion concentrations, right? And that is critical here because it's the ion concentration that is going to give us Q in that Nernst equation. So it is possible to do this, and when we construct such a cell where we have two half cells made up of the same materials but different ion concentrations, we refer to that as a concentration cell. The cell potential for concentration cells are typically very small, and those cell potentials decrease continually until the concentrations in the two compartments approach each other and they become essentially the same. So let's take a look at an example. So here we have two different half cells, or two half cells. The one on the left here has a zinc electrode in a zinc 2 plus zinc sulfate solution. Here the concentration is a 0.10 molar. On the other of 1 molar zinc ion. So we have the same electrode, same type of electrode, it's zinc in both cases. The difference here, though, is the concentrations of the zinc ion. So in one of these electrodes, we are going to have oxidation happening, where the zinc becomes a zinc 2 plus. And then in the other half cell, we have the reduction occurring, where the zinc 2 plus becomes the zinc metal. According to Le Chatelier's principle, we know that, or we can predict the following. We can predict that the tendency for the reduction to occur increases with increasing concentration of the zinc ions. Okay, so tendency for reduction to occur increases with increase, in this case, the concentration of the ion, the zinc 2 plus. So in the half cell on the right, which has the 1 molar zinc ion solution, we would predict reduction to occur here, which means then in the other one, in the less concentrated zinc, we would predict oxidation to occur. Okay, so we can write our cell notation. Okay, we have our zinc electrode, and then we have our phase boundary here, and then we have the zinc 2 plus, and here it's a 0.1 molar solution. This is oxidation happening. And then we have our salt bridge, the zinc 2 plus now, the difference here is the concentration. So 1 molar becoming zinc solid, this would be a reduction that is occurring. So we have our concentration cell made up of two half cells containing the same components, but differing ion concentration. So again, now we can write the equation for the oxidation. So the oxidation happening here is the zinc solid becoming zinc 2 plus, and that's 0.10 molar plus 2 electrons. And then we have our reduction occurring where the zinc 2 plus, which is now a 1 molar solution, gaining 2 electrons to produce zinc solid. Okay, so we add these two together, the electrons cancel out, zinc cancel out, we end up with zinc 2 plus 1 molar becoming zinc 2 plus 0.10 molar. All right, so now if we write our Q for the 0.1 molar divided by the reactant zinc 2 plus 1 molar. 0.1 over 1, which is 0.1. And we can plug that into our our Nernst equation. Okay, so now we know what Q is. Okay, so remember our Nernst equation. We have E of that cell is equal to E naught, and that's minus RT over NF ln of Q. So our E of the cell for a concentration half cell, okay, this is going to be equal to 0 because in the oxidation and the reduction, we have the same element. Okay, so the difference there is going to be 0. Ln of Q here would be ln of, what do we have, 0.1. And then we have our negative RT over N here. The number of electrons transferred is 2 F. So we can substitute these into our equation. What we find is that E here of the cell ends up being 0.030 volts. Okay, so this is how you would calculate the concentration or the voltage of a concentration cell. You need to identify what the concentrations are, and then the more dilute concentration, that is going to be the numerator. That's going to be the product side. The more concentrated one is going to be the reactant side. The denominator, we stick it into our Q expression, and then we just solve for E. So we can use that equation. Like I said, the cell potential for concentration cells are typically small. For these concentration cells. Okay, and they decrease continually until the concentrations in both cells decrease continually until the concentration in both cells equal each other or approach each other. Now remember, it's the difference in concentration that drives this process. So if there isn't a difference in concentration, then E of the cell is going to approach 0, right? So as long as there's a difference, we can predict that there will be a voltage. Now, one direct application of using concentration cells is to calculate. So these can be used to calculate KSP, right? Remember, we talked about solubility back in the earlier sections. KSP values for sparingly soluble salts are really, 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 really small. And it's very difficult to use other types of analyses to determine KSP values. Because the concentrations are so small, techniques like colorimetry or spectrophotometry are very difficult to use. And in fact, the concentrations of those ions, those sparingly soluble salt ions, are measured using these concentration cells. So let's take a look at an example of how that can be applied. So it says here an electrochemical cell is constructed for the purpose of determining KSP for silver cyanide. Okay, so we have AgCN solid, sparingly soluble will give us Ag plus, AQ plus the cyanide, Cn minus. Okay, and we know if it's a sparingly soluble salt, this KSP is going to be a very, very small value. So we have the product of Ag plus, Cn minus. We can predict this to be very small. And then this is determined by constructing a half cell. One of the half cell has silver electrode in a 1 molar solution of silver nitrate. The other half cell has a silver electrode in a saturated solution of silver cyanide. And then the cell potential is measured and found to be 0.470 volts. Determine the concentration of the silver ion in the saturated silver cyanide solution and the value for KSP for AgCN. Okay, so we need to find here the concentration of the silver ion. And then we also need the KSP. Okay, so we were given a couple pieces of information when we silver electrode, so Ag electrode over here, and that's a solid, and that is in a saturated solution of silver cyanide, AgCN. So this is going to give us Ag plus and Cn minus. And we're told that this is in a 1 molar. So, oh, I'm sorry. Backtrack a second here. Let me make sure I read that appropriately. So 1 half cell consists of silver electrode in a 1 molar solution of silver nitrate. So AgNO3, 1 molar. And the other half cell consists of a silver electrode. So we have a silver electrode over here as well. And that is in a saturated solution of silver cyanide, AgCN. Okay, now silver nitrate here, as all nitrates are very soluble, this is going to give you Ag plus and NO3 minus. Because nitrates are soluble, the concentration of the Ag plus here is going to be 1 molar as well. Okay, so we know then that this here is going to be the concentrated, this one is going to be the concentrated half cell. And this one here is going to be the dilute. So AgCN, right, is going to give us Ag plus and Cn minus, but we don't know what the concentration of these are going to be. So we need to figure that out. So the half cell with the higher concentration, which is the one here on the left, if you remember back from what we talked about previously, okay, we would have reduction happening at the higher concentration. Okay, so here we'll have reduction occurring. So we'd have Ag plus, and this would be a 1 molar plus an electron to give Ag solid. Then in the dilute example, we would have oxidation occurring, Ag plus Aq. We don't know what that concentration is, plus an electron. So we add these together. Again, we have our Ag, AQ 1 molar becoming Ag, AQ, and then we don't know what this concentration is. We'll just call that X for right now, X molar. So when we write our Q expression, Q here will be our dilute concentration, which is X over the concentrated one, which is 1 molar. Okay, so we have our Q. We know that E of the cell is going to be equal to 0. We can simplify, as we mentioned before, we can simplify the Nernst equation. So we have E is equal to E naught standard conditions minus 0.0592 volts over N times log now of, in this case of Q that we have. Okay, so we know N here, the number of electrons, this is going to be 1. E of the cell here for a concentration cell is 0. Okay, so we end up then with E, which I think we were given that value. Yes, so E of the cell was determined. We measured that as 0.470 volts. We know what E is. So this here is 0.470, and then E of the cell, standard E of the cell is 0, minus 0.0592 over 1 is the same as 0.0592 times log of Q. Okay, so we'll do a little bit of manipulation on here. We know that Q, like we said before, is X over 1. Okay, so we have 0.40, 0.47, sorry, 0 volts equals 0 minus 0.0592 times log of Q, and then we're just going to solve then for the term here that we want. Okay, so if we substitute that in, we end up with negative, let's see here, we get negative 7.939. Okay, so we end up, let's just evaluate this here. So we have negative 0.0592 times log of, so X over 1 is the same as X. We divide both sides by negative 0.0592. Okay, so we end up with negative 7.939 is equal to log X. So then 10 to the negative 7.939 would be equal to X. So our concentration here, or X value, ends up being 1.15 times 10 to the negative 8. And then that's molar, that's a concentration. So that is equal to the X that we're trying to find, which would be this value here, which is the concentration of the dilute cell. So this ends up being 1.15 times 10 to the negative 8 molar. Okay, so that is going to be our, what we were trying to find, the Ag plus concentration. And then our KSP, right, when we write our KSP expression that we did up here, it's just simply now the Ag plus, which is the 1.15 times 10 to the minus 8 times 1.15 times 10 to the minus 8, because this is happening here in a 1-to-1 mole ratio. So if we know this concentration, we also know the cyanide concentration. So we essentially square 1.15 times 10 to the minus 8, we end up with 1.3 times 10 to the negative 16. And again, KSP values for sparingly soluble salts are very small. Okay, and that's exactly what we found. Okay, so the concentration cells take advantage of differences in the concentration of the aqueous solution, even though both electrodes are the same material. As long as there's a difference in concentration, we can expect there to be a voltage associated with the cell. And an application of this is in determining both the concentrations as well as the KSP for sparingly soluble salts. So most of those values that we saw back in the earlier sections when we looked at KSP and solubility equilibria, are those really, really tiny values, right? They can be determined, they can be calculated by using a very, very simple technique. As long as we know how to use the Nernst equation, and as long as we know how to incorporate the reaction quotient into electrochemistry.